Hello, it's getting late now, but this is the last maths question of the evening. This is a video to help you out with complex numbers, and you will come across this in your merit exam. For the parallel circuit shown, determine the value of the current I and its phase relative to the 240 volt supply using complex numbers. Now, complex numbers have been developed to help us understand impedance and reactance in electronic circuits. They use the letter J, which is there to represent an imaginary number, because we find that the inductance and the capacitance work opposite to each other, and true resistance goes horizontally like this. The letter J represents the square root of -1, which can't be resolved, and J squared is the square root of -1 times the square root of -1, which gives us -1, and that would become important later. We're going to find the admittance, and the admittance is the impedance of each branch divided into 1. And we're going to find the admittance of each of these branches here. And we're going to start with the top branch, which is 4, and because it's inductive reactance, this is an inductor here, it's 4 plus 3J. So Y1 is equal to 1 divided by 4 plus J3. Now, to resolve this fraction, we have to use something that's called the conjugate of the complex number. And all that means is we take the complex number that we have and we change the sign in the middle, like that. And we multiply the top by the conjugate. If we multiply out these brackets, we get 4 times 4 is 16, minus 12J, plus 12J, minus 9J squared. The minus 12J and plus 12J cancel out, and we end up with 16 minus 9J squared. But here we can see that J squared is equal to -9. So -9 times -1 gives 9. Therefore, our whole admittance looks like this. Y1 is equal to, so we've got along the top, we've got 4 minus J3 divided by 25. And when I divide 25 into both terms, I get, and I've done this already just to save some time, so 25 into 4 is 0.16. Minus, because it's minus J3, minus 0.12 Siemens, like that. So that's your first admittance. The second admittance is actually really easy because there's no imaginary part, J part to the number. It's simply 1 over 10, which equals 0.1 Siemens. And then finally, the third admittance, Y3, we have 12 ohms, but because it's capacitance this time, it's minus J. So we have 1 over 12 minus J5. Of course, we put the conjugate in there, 12 plus J5, and the conjugate goes along the top as well, 12 plus J5, like that. And looking at what we did earlier, where we multiplied out the brackets, 12 times 12 is 144, and 5 times 5 is 25, so when we add those together, everything is divided by 169. 12 plus J5 over 169. And when we divide, always getting late here. So when we divide 12 by 169, we get 0.0701 plus 0.029 Siemens. And then all we have to do at this point is add all of our real parts and all of our complex parts together, all J numbers. So I'm going to line them up here. So we have 0.16, that's the first one there for Y1, 0.1, that's the one for Y2, and then for Y3 it's 0.701, 0.0701 to be more accurate. And we're going to add all those together. And then for the J parts, we've got minus 0.12 Siemens, and we have plus 0.029 Siemens. So the total admittance, I'm going to run out of paper here, so I'm going to write this here. You normally like to work neater than this, but the total admittance is going to be 0.3301 minus 0.09 J, like that. Okay, now to find now we've added all these together, but to find the impedance, we're simply going to find, this is our real part here, this is going to be 0.3301 there, and this is the imaginary part here. It actually goes down there, but it doesn't matter for the purposes of this anyway. 0.09 J, like that. And we want to find, I'm going to use that to find this, which is going to be the total impedance. So I've already done this on my calculator, but I will share it with you. When you square 0.3301 squared, those are minus, it actually becomes a plus. 0.09 squared, you end up with the square root of 0.117, okay, which is equal to, so if you did that sum, you would get 0.342 times 240. So what that would do is that would give you the current flowing through the circuit. So on my calculator, I'll just quickly do that. 0.342 times 240. 82, about 82 amps. Now, the other bit of this question asks you to find a phase, and the phase is this angle here. We find that with the tangent. So it's tan minus 1, or the inverse tangent function of 0.09 J divided by 0.3301, like that. So I'll quickly do that as well. 0.09, this 0.09 divided by 0.3301 is equal to, so it's tan minus 1.272. Remember, this is a minus here, by the way. Tan minus 1.272. Okay. So shift, we can see that, tan minus 1.272, 15.21 degrees, minus 15.21 degrees. So the phase angle here is minus 15.21 degrees. Of course, I've rounded quite a few numbers up because I want to get through this quite quickly, but that's the technique for doing it. And when you write this out as an answer, you're going to go 82, because that's the amps, and the phase angle minus 15.2 degrees, like that. Okay, so it's quite a complex question. There's quite a lot of maths in it, and it's easy to get lost actually, but that is the basic technique for working your way through to find the current and phase angle when you're given an AC circuit that has inductive and capacitive elements in it. Okay.